Hello scholars, welcome. Mr. Hinkle here. In this lecture, we are discussing surface currents as part of our overall discussion of the movement of water in our Earth's oceans known as ocean circulation. So let's get into it. We will analyze the effect of wind to generate surface ocean currents and then describe physical characteristics, which there are a few, of surface currents, and we'll look at different patterns of circulation in our various oceans to round out this lecture. So surface currents occur because wind blows. Wind is created by differences in pressure in Earth's atmosphere, and the friction of the wind on the ocean generates surface currents. These surface currents will transfer heat from the tropics to the polar regions. They influence local and global climate, and they are important for biological productivity and marine life in general. About 10% of the ocean water is affected by surface ocean currents, the friction between wind and ocean. Now, these surface currents are going to be affected by the distribution of continents. It would be a very different picture if we didn't have continents, that's for sure. Gravity, friction, and the Coriolis effect, the apparent deflection to the right in the northern hemisphere and to the left in the southern hemisphere for the straight line movement of an object. We'll get into that in detail coming up. So how do we measure? Well, we can measure directly by inserting a probe into the water. There's various types, and indirectly using satellites. This is pretty much the name of the game for observations when you're trying to collect data. You can have direct observations where you're actually measuring and recording using a variety of different instruments. In this case, we've got drift current meters, propeller type flow meters. You can also use data from satellites, radar altimeter, and here we have the ocean dynamic topography. Electronic equipment in Earth's low orbit, circling the globe, that collect a myriad of information that allow us to understand how these various systems work. We live in an age of information, and it's really, really cool. Okay, so there is a pattern to surface ocean currents, and the pattern is called a gyre or a subtropical gyre. So there are 5 subtropical gyres. There are more gyres. There are smaller gyres. Of course, the conversation gets a little bit more nuanced and complex, but gyres exist because of wind, Earth's rotation, i.e. Coriolis effect, and the shape of ocean basins, where the oceans are relative to continents. Let's look at these. I could draw them, but we'll just use our handy-dandy chart. This is the Pacific Ocean. This is the Atlantic Ocean. This is the Indian Ocean. Southern Ocean is down here. Arctic Ocean is up here. Map projection, the Earth is not flat, and it's definitely not a rectangle, but for understanding, here we are. Equator, right here. So in the North Pacific, we have this clockwise rotating mass of water. In the North Atlantic, we also have this clockwise rotating mass of water. In the South Atlantic, it's a counterclockwise, South Pacific counterclockwise, and Indian counterclockwise. So our rotating spirals of water move counterclockwise in the southern hemisphere and clockwise in the northern. We'll go NH clockwise, SH counterclockwise. Everything to do with the Coriolis effect. More on that to come. See my video, my balloon demonstration of the Coriolis effect, or my lecture on the Coriolis effect. So, the most famous surface current in the world is the Gulf Stream. Here you can see it using a temperature map. This is all warm water at the equator that comes up the east coast and then travels across the North Atlantic and makes its way, transferring heat. Ocean currents transfer heat and regulate global climate. This carries about 150 times more water than the Amazon River, the largest river in the world. That's an amazing fun fact. First mapped by Benjamin Franklin. He did all kinds of stuff. Good old Ben Franklin. Thank you for daylight savings time, although depends whether you like throwing off your schedule, your natural rhythms twice a year. And thank you for dropping some thermometers in the water to notice that there was a band of warm water. And so if this water is going this way, you want to be in the warm water traveling from America to Europe, and you want to be out of the warm water traveling from Europe to America. So practical applications about knowing how our oceans work. That is awesome. Biological hotspots. We have warm core rings and cold core rings, where as the Gulf Stream is, up here is better, cold core ring, warm core ring. Fishermen know these rings as great places to find schools of fish. They are an artifact of the physical properties of these surface ocean currents that are moving in specific ways, creating unique biologic populations. Okay, speaking of physical properties, let's go through some. So there was this phenomenon that was noticed by sailors when they were observing that the wind would be blowing from one direction, but the movement of the boat was in another direction. The wind would be blowing in one direction, but ice sheets and glaciers would be moving in another direction. Sea ice, I think that's the word I was looking for. I got confused when I said ice cubes, but sea ice. And so icebergs, there we go. I know what I'm talking about. So what's happening is, as the wind blows over the ocean, that friction is felt down into the ocean, but it's strongest here. And so the direction of movement underneath the ocean spirals in a circle, giving it, these are better, right? Giving it a net movement direction 90 degrees, but an actual movement at 45 degrees. So this phenomenon is called the Ekman spiral, the ability of the surface winds to be felt down in the water column spiraling in a circle. We'll put it here. Ekman spiral. And the actual movement of the water, Ekman transport, 90 degrees to the direction of the wind. How wacky is that? Pretty awesome, pretty cool. Geostrophic currents. So water flows downhill underneath the force of gravity. But there are areas where water is converging. And when water comes together, it pushes up. When water is higher than the surrounding water, it moves out. So we get what's called a geostrophic current. Areas where Ekman spiral and Ekman transport are accumulating water, you get a bit of a bulge, a bit of a high area that then is offset by the downward movement of water. Cool, okay, what else does water do in the oceans because of surface ocean currents? Well, glad you asked. Western intensification, and this is because our Earth rotates. So that means that the movement of the water tends to pile up water on the west side of ocean basins. Now, most things are going to be hemisphere specific, but this western intensification occurs in both the northern and the southern hemisphere because the Earth is only rotating in one direction, therefore water is piling up and you get more water on one side than the other side. Our Earth is cool. Our water moves. It's affected by the moon, That's great. These are important ones. These ones are wildly important for biological productivity. There's areas where Ekman transport causes divergence, which allows for upwelling to occur. In other areas where Ekman transport causes convergence, which does not allow for upwelling, it creates downwelling. So here along the equator, the winds blow from east to west. These are called the trade winds. The Ekman transport of the trade winds, reaching pretty far here, causes the net direction of movement away from the equator, creating upwelling to occur that brings nutrients from deep, nutrient cold water, allowing for high amounts of biological productivity. So, if you remember from our ocean circulation introduced, we said ocean currents are important for a few things: climate regulation, the movement of heat, nutrients, and gases, and supporting marine life. And now we're starting to figure out how and why exactly that happens. If we look at coasts, wind is coming us one direction, upwelling occurs. Wind is going the other direction, downwelling occurs. This is because of Ekman transport. Here, 90 degrees would be away. Here, 90 degrees would be towards, wind this direction. And so we get no marine life, no biological productivity where we have downwelling, and we get high biological productivity where we have upwelling. So this process we'll talk a lot, especially upwelling, when we get into our primary productivity chapters. But for our objective here today, we're talking about surface currents. Upwelling occurs because Ekman spiral and transport carry water 90 degrees from the direction of movement, thereby allowing the processes of upwelling or downwelling to occur. Okay, so Pacific Ocean, we got the North Pacific, we've got the South Pacific. They're made of specific currents. And look at this, the equator is hot. So the equator brings warm water down to the east coast of Australia, warm water up into Indonesia, cold water to North America, cold water to South America. So the west coast of the Americas are a little bit colder climate, colder and drier than the east coast of Australia, Indonesia, and Asia, all having to do with the transport of heat because of surface ocean currents. That's awesome. Let's go to the other side now. Here's the equator. This means that the east coast of North and South America, now these are going to be warmer waters with different climates. Africa and Europe are going to have cooler climates. Again, everything to do. Global climate and climates of various regions are going to be impacted and affected by the transfer of heat through surface ocean currents. Antarctica is a little bit different because it's way down. Where's my globe when you need it? Because it's at the bottom, these currents just circle all the way around it. You have the Antarctic circumpolar currents, the east wind drift. So wind blows, the friction of wind drags water. That water creates currents, thereby affecting climate and biology. Sounds so simple. The Indian Ocean is a little bit different. Okay, so we have monsoon winds that are coming from the land to the ocean in winter and from the ocean to the land in summer, thereby affecting ocean currents. This is a whole topic on its own, but you have a very high heat capacity differential affecting seasonal land weather, and that in turn affects phytoplankton productivity or primary productivity. So again, I'm trying to drive this point home that ocean currents help regulate climate and support marine life through the transfer of heat and nutrients around the oceans. Wind generates surface currents to form rotating masses of waters called gyres. The Coriolis effect impacts ocean currents. This thereby influences biological productivity and, let's just for good measure, regulates Earth's climate. Thank you so much, and I'll see you in the next one.